You write a program and you decide to make it multi-threaded program. You separate everything carefully without having any dependencies between your threads. And at the end, when you release your program, either in the testing server or the production server or on your local PC, you see that whenever you add more thread to your program slows down further. Although your variables are totally independent from each other, there's no cross threads between your threads, still you face this scalability issue. This could be one of the silent killer of the performance, which is known as a false sharing. This silent killer doesn't throw any exceptions. It's just killing your performance. But even with that issue, your code will run, but not the speed that you want from it. False sharing appears whenever several threads repeatedly modifies different variables that happens to occupy the same cache line in your CPU. Logically, they are not even sharing the data, but the hardware treats the whole line as the unit of coherence. So the threads force ownership over it, which means that both threads or several threads, they're going back and forth fighting each other to occupy this part of the hardware. So welcome back to what every programmer should know about the memory. Last time we talked about consistency models and barriers, and today we will face the silent performance killer, as we name it, false sharing. Imagine this naive C++ structure. So the structure stats, it has two counters, counter A and counter B. They're both defined as an integer. And in your program, you spawn two threads. One increment counter A and the other one increments counter B. Separate variables. It looks totally safe, right? On most modern CPUs like ARM64 or x86, the cache line size is 64 bytes. It's common size, but not guaranteed that all the architecture will have the same size. And since both variables are integers, and typically they will occupy 4 bytes for each of them. So they will sit in the same line. When thread 1 writes counter A, it must obtain that line in a writable state, either as a modified state or exclusive write. This will invalidate any shared or clean copy of the entire line in other core's caches. When thread 2 then writes counter B, it has to take the ownership, invalidates thread 1 copy, and tries to write its own. And this ping pong will continue between these two threads. Important note here is that the second core usually doesn't fetch from DRAM every time. With MESI or MOESI, the most recent copy can transfer directly core to core. The cost is still high. As the name comes, is that it is false sharing because logically those data are not shared between two threads. And the symptom for your program is that you try to scale your program, but you get to the plateau performance before even you expect it. And that doesn't show as a bug. Let me show you a real world example. Here is a simple benchmark C++ code that spawns 4 threads, and each thread increments its own counter. So we have the structure aligned as 64, and we name it as a padded counter. So the value inside of it is defined as an integer, but it's atomic. We defined 4 counters from padded counters, and we defined the worker function in a tight for loop that each counter increments its own value. So in the main program, we spawn these 4 threads with their own counters, and we run the worker for each of them. So if you remove align as 64 and just use the plain atomic integer value, you will see that the performance degrades dramatically as you increase the number of threads. That's because all those integers, they will get packed next to each other, probably even in the same cache line. And congratulations, you will face the false sharing. Try running this with perfstat or simple time function to measure how long it takes. Then add a padding or alignment to see how the difference can be. Sometimes in your program, the difference can be even go to the 10x scale, just from avoiding unnecessarily cache line bouncing. Let's take a step back and understand the hardware behavior. CPUs do not load memory byte by byte. They load chunks, which is called cache lines. And the size of the cache line usually is 64 bytes. So when you access counter A, the CPU loads the 64 bytes, which is including counter A and counter B, and also potentially other variables. If another core modifies anything in that line, the whole thing will get invalidated. It has to refetch it. And that's cache coherence. This is usually a good thing. It makes the shared memory consistent. But when two threads modifying two separate data and those two separate data are within the same line, they start fighting. The cache coherence protocol will go to the overdrive, bouncing lines back and forth between different cores. And this thing becomes a scalability one. But the question is that how can you identify fault sharing? You might see a few signs or a few symptoms. You may see that your multi-threaded program scales well to the 2 or 3 threads, and then it stops. CPU usage is high, but throughput doesn't improve. And when you look into the memory bandwidth, it looks fine, but nothing moves faster. This is often a fault sharing symptom. On Linux, you can use tools like perf-c2c, which stands for cache to cache, to track fault sharing patterns. This will show you which cache lines are bouncing between the cores the most. If you see high traffic on the variables that shouldn't be shared, you have probably hit fault sharing. Intel vTune and AMD UProf also have fault sharing detection. These tools can highlight source lines or data structures involved in cache contention. Okay, so we know what fault sharing is and we understand how we can track it. How can we stop it? The answer is padding and alignment. The idea is simple. Keep the variables that are written by different threads on different cache lines. In C++, you can use align as 64 or hardware destructive interference size if your standard library supports it. This forces the compiler to space out your data. You can also manually insert padding into your data. Like in this example, the structure, it has atomic integer value with the char variable of the padding, which has the 60 bytes. And in total, the whole structure will have 64 bytes. Or for more clarity, you can use a structure like that. You can define the align as 64 for your counter. Then in your structure, you can define only your variable. And don't forget, arrays are dangerous. If you have, for example, the array of counters, even if each thread accesses its own index, those elements are next to each other in the memory. You have to manually align or space them out to prevent the overlap in the same cache line. Languages like Rust and Golang also provide tools for alignment. And in Java, this is trickier to do, but not impossible. You can use wrapper objects or specific JVM flags to adjust field layout. The point is, you should know where your data lives, especially in multi-threaded programs. Fault sharing is one of the most frustrating performance killer because your code is logically correct. It's doing everything right, but the hardware sees something totally different. So you're dealing with the hardware. 2 threads, 2 variables, 1 cache line, and now they're stuck in the loop of eviction and reloads. The fix is not always complicated. Sometimes it's just a matter of padding and alignment. But knowing what to look for, that is the real power of the program. And once you understand the cache lines, memory layout, and thread behavior, you can unlock the real performance of multi-core systems. If this video helps you to understand fault sharing, give it a like and subscribe to the channel to not miss the next video. And put your opinion in the comments if you have experienced fault sharing in your multi-threaded program. Until the next video, good morning, good afternoon, and good evening. Bye.